Okay, so in the last class, we started looking at small signal parameters. Okay, so the two parameters that we looked at was GM and R naught, and we also defined each of these parameters with respect to the Q point. Okay, and later we defined this GM to be defined as something like K n dash W by L VGS minus VT, where this value of VGS is based on the Q point that I'm fixing it, and even with respect to the R naught, we found that it is defined as lambda times ID, where this ID is again based on the Q point at which I'm operating in. Okay. Now, apart from this GM expression, we also found that there are two more forms, right? So what are those two forms? Two ID by UOV, and So these are the other two forms that we have apart from the first form of our GM. Okay. So now later what we did is that we were using the small signal model. We were trying to build the small signal model using our GM as well as R naught. Okay, so before we begin doing that, or begin using this parameters in order to build the model, we went on to this composite signal. Okay, so we defined something known as a composite signal, where this is a signal where it is composed of two components. One is the DC, which I represent with capital letter, and the other one is the small signal VGS. So similarly, I can even define the current, drain current, as a composite signal, which could be again defined as two parts, which is ID, the DC current, as well as the small signal current. Okay, so now after this, what we did is that in order to build this small signal model, which among these two parameters we were considering when we tried to build the small signal model? Are we considering this, or this? 1, 2, and 3. So which of these parameters were being taken into account? 3, the third one, right? So when I'm trying to discuss about the small signal model, we are concerned about the AC quantity here. Okay, so we are not worried about either this or this. Clear? But in order to derive those parameters like GM and R naught, I obviously have to rely on this capital VGS and capital IDs. Okay, so that is a different story. The small signal of VGS is actually related to our ID through some sort of relation. So what is the relation that we have between this VGS and ID? How is this ID being defined, small signal current? Through GM. So similarly, we also had a relation between this VDS and this ID, and they have been related by R naught. Okay, so again, R naught is a small signal parameter through which I am trying to define. Okay, so in short, I have this ID that could be written as GM times VGS, and the same thing could be done for this, but this time it is having an inverse relation. So now today what we are going to do is that we are going to find one more relation with respect to the ID. Okay, what happens when I have a variation across the body and the source? So how is that has been going to get related to this ID? Okay, so this impact could be modeled by, or the relation could be defined by something known as GMB. So this GMB is nothing but the transconductance, but this has a special name or different from the transconductance we have spoken before, and this is called as body transconductance. And one could use the same analogy over here in order to define this current. Just because of the variation of VBS, I am getting a current, and that current could be modeled as GMB times that of VBS. Okay. So now in order to talk about this body transconductance, I first physically mean it, and then later we'll talk about this small signal parameter. Okay, so let me take a device level quantity, and then we'll talk about it, and then later once we derive the theory of it, and later we'll use that theory in order to build the ID versus VBS graph, and from there we'll try to extract the small signal ID with respect to VBS. Is that clear? So let me begin with this physical structure. From the physical structure, we'll derive the large signal and from the large signal we will derive the small signals or small signal parameter. Okay, so this is the relation that I'm going to do it right now. Now let me consider an NMOS transistor where I have this source and the drain and the metal and the oxide, and the type of substrate that I'm going to have is going to be a P substrate for an NMOS transistor, which is an enhancement type structure, right? Yeah, so let me define the value of threshold voltage. Okay, so what exactly the threshold voltage is all about. Okay, now in order to talk about it, I'll just fix some initial conditions. So I'll just have this VD somewhere around 0, and what about the body of our NMOS, where it will be tied? From the DVD you would have learned. Yeah, source can be any potential, right? So in general, a body of an NMOS is connected to the lowest potential. Okay, rather than telling as a ground, we will consider as the lowest potential in our circuit. Okay, so obviously it is ground, it's fine. So I'm just going to connect the body to the ground. So we'll also have some sort of structure like this, and then that structure is going to be connected to our ground. Now let me also fix my source potential, which is at ground, and I am going to vary my VG. Okay, so I'm just going to vary this VG right from 0 all the way till VT. Okay, so lesser than the value of VT. Now what happens in this particular process when I'm trying to vary the value of VG between 0 to VT? So this VG is a positive quantity. Is it a positive quantity? Why no response? It's a positive voltage, right? Yeah. For an NMOS, again, VT is a positive quantity. You all know it. So the moment I try to place, say for example, I have just incremented a voltage by 0.001 volt. Okay. So what happens is that it lands a particular hole on the metal surface. Okay, so what would happen in this particular case? What happens in right now? I have a dielectric medium between the metal and this oxide, and there is a substrate. What type of substrate I have here? It's a P substrate. So what type of carriers I'll be populated with? Holes. So what happens when you have two kind of similar charges placed each other? Yeah, so they will be repelled off, right? So when it repels, what happens is that it leaves out an ion which is a negatively charged. Am I right? Yeah. So now what I'm doing is that I'm just going to vary this VG all the way closer to VT, but still not equal to VT. Okay, so which means that I'm trying to place more number of holes on the metal plate, and due to which it has tried to deplete the charges here. Okay, so I have to have a similar number of holes in order to have this, right? Yeah. So now I'm just going to call this as a depleted charges, okay, QD. Now what happens is that the moment I try to reach the value of VGS that is exactly equal to VT, then what could happen right now? Now again, the number of negative charges depends on the number of holes that I have on the metal, okay. So it is something like this kind of phenomena would happen, okay. So now basically we supposed to understand that the threshold voltage is a function of QD, or the depleted charges that I am having. Am I right? So how will I emphasize this particular phenomena? So when I'm closer to the value of VT, what I have across the channel is the depleted charges, and what I have across the metal, a positive charge, and that positive charge is exactly a mirror of my depleted charges. Okay, and the moment I cross this VT, so what is happening is that I have created an inversion layer between the depleted charges and the interface between the metal, so between the oxide and the semiconductor, okay, over here. So here I just try to create an inversion layer. Does this make sense? Right? So in short, I can say that the VT is generally a function of the amount of QD that I have. Okay, just because I need to mirror these negative immobile ions over here, right? So this is exactly the same number of charges that I have supposed to be mirrored on this metal before I actually achieve the value of VGS that is equal to VT. Okay, just before the value of VGS that is equal to VT, I have to have the exact mirror of whatever the charges, the number of charges that I have for the QT has to be mirrored over here. Okay, so it is an exact mirror of QD that I have on the metal plate with positive charges. Okay, that's the reason why we can actually tell that there is a kind of relation, or VT is basically a function of the amount of charges that I have across the QD or the depleted region. Okay, if you can say okay, then I can move forward body effect after. So you are clear with it. Yeah. So now what I do is that I'll just pull this VB towards negative potential rather than fixing at 0. Let me try to move this particular potential VB lesser than the value of 0. Now right now what would happen in this case? Yeah, so I'm just trying to place some sort of negative charges on these plates, okay, where I have a body terminal, and when I have a negative charges and across this P substrate I am been filled with the holes. What would happen when I have opposite charges? They tend to recombine or attract each other. Okay, so due to which when I lose some of the holes, what happens at this particular QD? Will it increase or will it stay as it is, or will there be any change first of all on the QD when I'm trying to lose some sort of holes in my P substrate? Obvious, right? The QD obviously has to increase in order to accommodate that. Okay, so now the QD amount has got increased, and right now in order to reach the value of VT, or in order to make the inversion to happen, what I supposed to do on the metal plate? I have to place more number of positive in order to reflect this entire QD that I have. Okay, so right now currently I have more number of QD or the depleted charges, and if I want to turn on this particular channel, I have to have an equal mirror of positive charges on the metal plate. Okay, so which means that I need to have a more positive voltage in order to land more number of holes on the metal plate. Is that making sense for you? Yeah. So that is the reason why the moment we have this VB that has been lowered, our threshold voltage is getting raised up. Okay. So that is the impact of the body effect. Okay, fine. Okay, so that's fine. So whenever there is a body effect, we say that the threshold voltage is being increased, and in general one could model this threshold voltage as something like VDH that is equal to VDH naught gamma square root of 2 phi f plus VSB minus square root of 2 phi f. Okay, so this is the formula that I supposed to write it on the day I guess I was talking about a relation between the ID and VGS. Okay, so we ended up having some crappy threshold voltage expression, but this is the right expression. Okay, yeah. So now what I do is that let us try to understand the behavior of this equation by some sort of small exercise problem, and then later we'll just try to build the small signal out of it. Okay, so what I do is that let me try to have something like this, and I have this Vx or Vb, so now that I just want to plot a relation between this ID that I am plotting, or the current that is flowing through the drain terminal, and this Vx or Vb, sorry. Okay, now this time I'm just going to look at the negative potential, okay, negative side of this VB, and what would happen under this condition. So when the value of VB is equal to 0, will there be any current through the device? What is this VDH naught basically means? Yeah, so when I have VSB that is equal to 0, which means that when the source and the body are at the same potential, then this is the threshold voltage that I will be having for the device. Okay, now the point is that when I am having here, I have the threshold voltage which is 0.6, and I have VGS that is equal to 1.2 volt. Am I right? So under this condition, will I have some sort of, and even VDS has also been given, right? Yeah, so will I be having some sort of current through the device? Yes, obviously. So let us fix this kind of current somewhere here. Okay, so this is the default current that I have when I have this body exactly at the potential of source. Okay, now what happens the moment I try to vary my VB towards the negative side? Yeah, so based on this expression, what happens is that as I increase the value of VB, what is happening is that in the negative side, okay, so let me write it as decrease in the value of VB, so that what happens to the VSB term? It increases. Okay, why? Because VSB is nothing but Vs minus VB. I'm putting a value of VB which is a negative value, so due to which the negative into negative will become positive. Okay, so the entire VSB is getting up. Is that making sense for you? Yeah. So say for example I have minus 1 volt, which means that it is getting added up. Okay, and my source potential right now according to this question, it has been fixed at a voltage which is equal to 0, so due to which my VSB is taken as plus 1 volt. Okay, so please be aware of that. Yeah, so just because this VSB is rising up, the threshold voltage of the device will also rise. Okay, now what happens to the current? Will it increase or decrease, or will it stay constant as it is? It has to decrease, right? Because current ID is basically proportional to VGS minus VT, and if this quantity is getting reduced, obviously the current value also has to get reduced. Okay, so now again, in which region right now we are operating in, according to the conditions that we have placed, it will be in the saturation regime, right? So due to which I can even put a square on it. Okay, yeah. So now how would I draw this relation? What kind of graph that I would get? Obviously we know that we got an answer that the current has to reduce, but what type of graph that I need to plot? Okay, so it's a linear 1, 2, 3. So there are 3 options here. The third one. Do you all agree with it? Yeah. So just because of the square root, and then later on it's been evaluated with the square, so do not get confused with those terms. So we'll get the expression which is similar to 3. Okay, so I would get something like this. At a particular value of VB, let me mark that value to be VB1. What happens is that the current goes to 0. Okay, can we able to identify the value of VB1 from the given data that is available here? Then yes, so the current ID will go to 0 the moment the value of VGS of the device is exactly equal to VTH. Okay, now what is the value of VGS that I have for the device? 1.2. So what I do is that I will just fix that value of 1.2. Okay, and I know this value which is VTH naught, which is 0.6, and I know the value of gamma, which is 0.4, and I have the square root of 2 phi f, which is given as 0.7, so I substitute that, and then I have this VSB. Later on we'll write it in a negative quantity, that's fine, and then I have the square root of 0.7. So I just want to extract the value of VB out of this. So if anybody has got the answer, please let me know so that we'll move on to the next one. 4 point, yeah, it is minus 4.7, okay, 75. Okay, that is the value that I would get out of this calculation. Okay, yeah. So now that it's a negative value, and if I want to plot the same graph with respect to VSB, how would this graph would look right now? I just want to plot the same graph, but instead of VB, I just want to plot it as VSB. So how would this current graph would look? So right now the current graph is in the negative scale. Okay. Now what if I'm changing this x-axis from VB to VSB? It mirrors, right? So it mirrors something like this. Okay. Yeah. So now let me take a circuit condition and then let me fix our bias point, and then graphically we'll try to evaluate the value of GMB. Okay. So I have this NMOS transistor where I'm fixing the value of VG or VGS, and then the source node is given a positive quantity, and I'm fixing at a particular Q point, and then the body of this device is fixed to a ground. Okay. Now the same similar condition would reflect the same kind of graph. Okay. So even this circuit condition would then reflect the same thing. Okay. Now there is a kind of current that flows through the device. Okay. So currently I will mark it as Q just because I'm fixing the bias voltage for the VSB. Okay. Now these 2 points, that is IDQ and VSBQ, could be marked on this particular graph. Okay. So let me choose this VSBQ somewhere here. Let us fix it here, and this would mark my Q point of the device. And what is the corresponding IDQ value that I would get? The intersection of this line with the graph should get us the IDQ, right? So this is the base at which the current would flow. Now what I do is that around this particular Q point, so let me mark this. So let me have a composite signal here, and over time I'm just going to have a wiggle around this particular Q point. Okay, and let me even mark this. So this is my IDQ value, the base value. Okay, and this is my composite signal thing, and over this I'm just going to have a wiggle. Now obviously the top of this graph would then hit this particular graph and gets reflected in the negative axis or the negative side, right? So there is a kind of inversion that is happening. Whenever there is a positive cycle on my VSB, it is getting reflected in the current as a negative value, okay, or a negative cycle. Okay, and whenever I have the negative cycle, this gets reflected as a positive cycle for the current. Okay, so again how I am getting is just by interpolating this minimum value onto the graph, and from the graph I am extrapolating the value towards the y-axis. Clear? No. The point is that I am fixing the value of VGS and VDS to a constant value, and that is the assumption that we have to use it. Yeah, the AC current is flowing because of the VSB, change in the value of VSB. I'm trying to have a wiggle, means like I'm trying to add a small signal around this particular Q point, but I'm not adding anything here. This is not creating the small ID. Okay, this is fixed to a value ID. Okay. Yeah. So this wiggle is what I have to mark it as small signal VSB. Is that clear? And due to which the current right now would turn from this to small ID. Okay, so because of this wiggle, addition of wiggle, there is a change in the current, and that change in the current is being marked with small ID. Okay, yeah. So now there is something that we have to come up with it. So what is happening is that as I increase the value of VSB, what is happening to the ID according to the graph? It is decreasing. So the current is getting reduced, and the same similar thing could be marked here. The ID would then be related to my VSB with some sort of parameter, and that parameter is what I said is GMB. Okay, is that clear? Any doubt in this expression? I'm expressing the small signal current ID that is purely flowing just because of the change in the value of VSB, and that small wiggle is what has been marked over here as a small VSB here. Okay, and the relation that they share is through this parameter GMB here. Okay, is that clear? And there is a negative sign that is sitting. Now can I able to remove this negative sign? If we swap the polarity of my VSB, rather than reading it as VSB, let us try to read it as VBS. So what happens is that the ID would then be written as just GMB. Okay, so ID is equal to GMB times that of VBS. Now there is a reason why we are using this notation rather than this previous notation, is that when I look for the expression of the change in the value of ID just because of the change in the value of VGS, we had a relation that ID is equal to GM times that of VGS. Okay, so here this VGS is nothing but VG minus VS. The source was at the end. Even here, when I look for this, I could able to split this VBS as VB minus VS. The source was taken as the reference node. Is that is clear? So that's the reason why it is better to follow this notation such that it maps the similar kind of notation for the current relation with respect to VGS. Is that is clear? So we'll follow these two notations for our rest of the course. Any doubt? Or am I confusing you people? I'm just swap the variables, nothing else. Okay. So in a sense, this has been written. Okay, so I don't want to confuse you further. So this is the notation that we'll be using. And right now, let us try to evaluate the value of GMB. Okay. Now, currently, I could write this GMB as ID by VBS in terms of small signal. But I can also express the same quantity in terms of derivative, right? First order derivative. How would I express that? Dou composite ID and derived with respect to what? VT or, so what is this quantity? It's a small VBS that wiggle around this Q point. So I have to differentiate around this Q point, right? In order to get this wiggle. Differentiation is nothing but how much this VBQ is getting varied around that particular Q point, okay? And that is what I am trying to measure. So it would be dou ID by dou VBS. Is that is clear? This is the same phenomena that we did even in the last class. Even for this, the GM was expressed as something like small ID by small VGS, or in short, it is returned something like this. Okay, so this VGS and this VGS is supposed to be same, right? So we are trying to measure this wiggle just by taking the differentiation around the Q point. Okay. Being silent makes me afraid, like whether you people are really understanding and then coming along with me or getting stuck somewhere. If you have any doubt, you can ask. No, until otherwise you ask, I cannot predict your doubts. So, any doubt in this? Okay, not. What about others, remaining class? You have to ask, otherwise I don't know what doubts you have in your mind, right? I cannot read your mind. What is that is not clear here? At least for the people, those who are attending from the last two classes has to understand this, because we did the same thing. We didn't do anything over here, or at least who have watched the video, which is up in the YouTube. Hope that it is clear. Can I agree with it and can I proceed? You have to ask, otherwise it would be like Greek and Latin. Okay. So just because of lack of time, I'm just trying to rush up. So now let us try to derive the value of GMB with respect to dou ID by dou VBS. Now, what is the expression of this ID? So whenever I'm trying to talk about a small signal, which region I have to assume that this device is operated in? Saturation. So what current I have to substitute here? Current equation that I use it normally for our saturation region, which is half Kn dash W by L. And what type of signal I have to substitute here? VG. Do you really think, because when I'm trying to evaluate this GMB, I'm going to assume that the VDS and the VGS are fixed to a constant value. Even we did the same analysis that I'm fixing the value of, when I try to evaluate the value of GM, I said the VDS was fixed to a constant. Okay, so all of the potentials which are not taken into account is assumed to be at constant. Okay, so it is being kept at the constant, so due to which this has to be returned as capital VGS. Okay, that is making sense for you? Okay, so please watch the video in case if you are not getting it. And over here I will just put it as capital VT, just because we know that it is getting varied, but I'll just put it like this. Okay. So now let us try to differentiate this. So due to which what would happen is that there is something like x square, and due to which kn dash w by L, and then what I have is something like VGS minus VT, and then followed by this, what I would have. No, it is not the DC component, it is a composite current component that I'm using it. Yeah, but inside this VT, it is not exactly VT naught. Okay, it is not VT naught, it is just VT or VTH. Okay, now just because I'm trying to differentiate this, is there any extra term that I need to add it here? Yeah, so what is that? Into? Not gamma, but we will just go for differentiation. So what happens is that there is a negative value popping out just because of this negative sign, dou VT by dou VBS. So now that what I do is that, let me try to have this expression alone. Okay, so I just substitute dou VT by dou VBS, and we can write down this expression of dou. Okay, so how do I expand this? It is nothing but VTH naught plus gamma, and then square root of 2 phi plus VSB minus square root of 2 phi f. Okay, yeah. So what is the end result that I would get out of this expression, or out of this derivative? I think you know, when I try to differentiate square root of x, what I would get? Yeah, something like this, right? Or did I forget anything? Yeah, 2. Right? So just because our VSB is sitting inside this, okay, but what I'm trying to differentiate is VBS, but what expression is sitting inside is a VSB term. So what is the final output that I would get out of this? Yeah, there is a negative sign, gamma, and this expression which acts as my square root of x. So due to which I just substitute here as twice square root of 2 phi f plus VSB is what I would get. Now already there is a negative sign here and there is a negative sign here. So what happens when I multiply negative sign with a negative sign? It becomes a positive quantity. Okay. Now there is something that I need to observe on this particular expression. What is this expression? Kn dash W by L VGS minus VD. It is nothing but our GM, the small signal parameter GM. Okay. So I'm just going to combine all of the results and then put it in a form which you are all familiar. So I'm just trying to evaluate for the expression for the GMB, which is equal to GM times that of dou VT by dou VBS, and the final outcome of this is nothing but gamma times that of square root of 2 phi f plus VSB. Is that all clear? Now normally, rather than writing this whole complicated expression, I would substitute an eta for this expression. So eta is nothing but gamma divided by 2 square root of 2 phi f plus VSB. Okay, and usually the value of this eta is always lesser than the value of 1. Okay, so due to which the back transconductance will be always lesser than the value of normal conductance. Okay, so I just want to see how this particular expression gets fit into our small signal model. Okay, and in order to demonstrate this, what I do is that I will just go so right now my current task is to draw the small signal model for this expression, which is ID equals to GMB times that of VBS. Okay, now in order to draw this model and make sense for you, what I do is that I just go with a device which doesn't have any body effect. Okay, so which means that I'm just going to have both the source as well as the body at the same potential. Okay, and I have the small signal. Okay, so I'm not drawing the entire model of this, but let me have some small signal around this VGS. Clear? Now according to this, the source as well as the body were fixed at a value of 0 volt. Is that clear? Now let us assume that I am trying to have a VGS that is equal to 100 millivolt. Now what happens when I have this positive 100 millivolt across this VGS potential? Is this all clear? So what I'm trying to map here is a voltage axis, okay? And the body and the source were fixed to a 0 volt, okay? So this is my axis, which is representing a 0 volt, okay? Or if you want, I will put it in a positive axis itself. Okay? So both the source and the body were at the potential of 0, okay? Now what happens the moment I try to feed a value of VGS that is equal to a positive 100 millivolt? What happens to the gate? The gate voltage would be shifted up by 100 milli, right? So this will be at 100 millivolt. The gate would be at 100 millivolt, okay? So this 100 millivolt, let me model it as something like I am having a ball. The radius of this ball is 100 millivolt, and I'm just placing the ball on the surface where the surface is a very hard surface, okay, which is at the ground potential. Does that make sense? So what I have is a very hard surface for the source potential, and due to which it lands exactly on top of this source node, okay. Now let us do the same thing where I have a different type of circuit. I have a source, and right now let me try to talk about the VGS, okay. So the body is at ground. So now according to this, let me mark your axis for the voltage, and this is my 0 value. And where is the body right now currently fixed? The body is fixed to a ground potential, right? So the body is fixed actually, but is my source is fixed to a ground potential or something else? Yeah, something else, right? So in this case I cannot do anything until otherwise I specify some value here, okay? So now what I do is that I just specify that my value of VGS is currently a positive 100 millivolt. Now it is something like I have a bucket of water, okay, where this water represents, the level of this water is actually representing my source potential, okay. Now I have this 100 millivolt which is represented by this VGS, okay. So it is actually a ball of a height of 100 millivolt. Now what happens when I try to land this 100 millivolt on top of this water? Will it sink for a small distance, or it will stay on top exactly? Will it be something like this, or will it go something like this? 1 and 2. So which one is right? The 2 one. It's a very well-known fact, right? So the ball cannot stay at the top until otherwise the surface at the bottom is fixed, okay? So it is something like a kind of watery kind of thing. So what happens is that you could able to see I have still the same potential difference of 100 millivolt. There is no change at all. There is no change in the radius of my ball. But what is happening to the source right now? The source, which was at 0, is being pushed towards the negative value, or is being pushed away from my 0 volt in the negative direction, and my gate is still at the positive potential. Is that making sense for you? Okay, so now let us try to put the entire thing in a kind of picture. So I have a gate potential and the source potential, and when I try to measure the voltage difference between the VGS is the same 100 millivolt. But what is happening is that the source is being pushed towards the most negative potential, and the gate is at a positive potential. But what about the relation that I have between the source and the body? Is the body is higher than the source or smaller than the source, or exactly the same potential? Higher. So the gate would then, the body would then receive a positive notation just because I'm just comparing VBS. So yeah, VD. That we will not consider right now. As of now, I'm talking about the phenomena in order to draw the small signal model of it. Okay. So what I'm trying to do is that I'm trying to measure is my VBS is a positive or negative. Okay. So which means that in this case it would be a positive quantity, and when I try to measure my VGS, it is still the same positive quantity. But this value is not exactly equal to my VGS. That is for sure. Okay. So it's all making sense. Yeah. So now let us, with this analogy, let us try to build the small signal model.
How are you saying that the source potential is?
Because since it is not being fixed, it can actually float. And whenever I have this positive cycle, the gate is higher than the potential of my source, and that is how I push the source terminal towards the downside. Since because I'm assuming that the VGS is a positive quantity. Okay. Yeah. So now let us try to draw the small signal model of this circuit. Okay. So as I said, I'm just going to pick all the elements of the source and the drain, and I also have a body. Okay. Now we know that this body is connected to the ground. Okay. Now I have this VGS, and due to which I have the polarity as plus and negative. Okay. So which means that I'm talking about a positive cycle of my VGS. Then how will I draw the current that is flowing just because of this VGS? How will I represent the current? Yeah, it would be downwards with the value of GM VGS, right? So what I do is that I try to represent this with a current GM times VGS. Okay. Now how do I draw the current direction of my GMB VBS? Because the source is not exactly at the ground, so how will I draw the current due to the body effect? Will it be downward or in the upward direction? So the point is that why did I draw the current from drain to source? Just because the gate was at higher potential than compared to the source. Okay. So the current will flow towards the lowest potential in the circuit. That is a term that we used in the last class, right? So even here I said my VBS is a positive quantity, which means that the body is at higher potential than compared to the source. So the source is the least quantity that I have. So because of this VBS, there is a current that flows between the drain and the source, and it follows the same current direction as I had for my GM VGS. Is that clear? But this quantity is happening just because of my VBS, and this VBS is again a positive cycle. Does it make sense? Any doubt? Okay, so now let me just have a quick discussion. What if I'm talking about a negative cycle that is happening across my VGS? Okay, I'm just considering both the composite and this one. So what would happen when I try to map this particular kind of signal for this VGS that I'm talking here? I cannot write it as VGS, but yeah, still. Yeah. What happens right now when I'm talking about a negative cycle? So what happens to the polarity when I'm talking about a negative cycle of a VGS? They get inverted, right? Okay, so whenever there is a negative cycle, the polarity would then get inverted as negative here and a positive here. Now for this, how will I draw the current of GM VGS? Will it still follow from drain to source? No, because last class what I said is that for the current that I'm drawing, which is the small signal current, this small signal current will always follow the polarity of my VGS. Okay, so based on the polarity only I can draw whether it is flowing from drain to source or source to drain. It never depends on whether I'm working with the PMOS or NMOS. Okay, so in this case what happens is that the source is the most highest potential in my circuit, okay, compared to my gate. Now due to which I am plotting the current direction in the upward direction, which is flowing from source to drain. But what happens to my GMB VBS? So what I said is that the source is the most highest potential, but so in this case the body would then become a negative. Okay, because you can use the same analogy. You can still use the same analogy. What I said is that rather than having this gate at the top and the source at the bottom, this time the source was shifted towards the higher potential than compared to the gate. Okay, so now what I'm trying to read is the potential difference between the body and the source. So this VBS is read as VB minus VS, but VS is much larger than the value of VB just because VB is fixed to a 0 volt and I'm trying to have a positive quantity for this VS. So due to which I will have a negative quantity. Am I right? I hope that you people are following it. Okay, so in general it's a negative quantity, and due to which even the current of this would then follow the same direction as that of my other current source. Okay, so in case if you are not clear with this concept, you can always assume that whatever the current direction that you are drawing for this GM VGS, you use the same current direction for GMB VBS. Okay, does this make sense? Yeah. So what is the spending for the small signal model? The one is GM, the other one is GMB. What else we learned? R naught. Okay, so I just need to add this R naught somewhere between the source and the drain. I'll just fix it here as R naught. Okay, let us have a quick fun. It's again about this large signal analysis. So in the first diagram, I'm going to assume that the source and the body are shorted. Okay, so let me just use it. So this is without body effect. Okay, so now under this condition, I'm just going to vary the value of Vn over a time from some value to a different value. Okay, say for example from 1 volt to all the way to 2 volt. Okay, so that is why I'm doing it. Now I just want to read out the reaction that is happening for my Vout. This is my Vin. I just want to plot a graph for a Vout. How will I draw this? What type of structure is this? Is it a common source or common drain or common gate? Common? Yeah, drain, right? It's a common drain. It also has a special name along with it. What is that special name? Source follower. Okay, so now what do we really mean by the source follower name? Why did I say it's a source follower? Why is that name has come? Whatever the gate, the source terminal will follow the gate potential, right? But obviously there will be some sort of offset, right? Can you figure out what would be the offset? The question here is that should I need to draw this Vout on top of this or below this or something like this? Okay, I have 3 options. Okay, just because you said it's a source follower, my Vout would follow my Vn. That's it. Okay, over time. But the point is that whether I need to place the Vout on top of this Vin itself or below this Vin or above this Vin. What I have attached to the source node, there is a current. Okay, if you want to draw some sort of current through the device, there is a need of a particular value of VGS, and over this entire period I'm not going to vary the value of I1. So this quantity is a constant, which means that the value of VG is supposed to be held constant. Okay, so say for example I need to have the VGS to be equal to 2 volt for a current value of 1 milliampere, something like that. Okay, now I want to make sure that the difference between the gate and the source supposed to be held at 2 volt to draw a current of 1 milliampere. Now what I'm trying to do is that I'm trying to vary this guy over a period. Okay, so right from this value, I'm trying to vary the potential of my Vn. How will I draw the voltage graph for the Vout? Are you not clear? It's a very basic phenomenon I'm talking. What's supposed to be the potential difference at this particular point in time? It's already time up. Yeah. So between this Vg and this Vout is nothing but my source potential, right? So between these two guys, what's supposed to be the potential difference? No. What did I say? To draw a current of 1 milliamperes, I need to have a VGS potential difference between the gate and the source to be at 2. So the potential difference between the gate potential and the source potential is supposed to be equal to 2 volt. Okay, so say for example my gate potential currently is at 3 volt. What's supposed to be the potential at the source? 1. If I change this one to 4 volt, what's supposed to be the potential at V out? 2. Okay, so that's the reason why I have to draw this graph with a voltage difference of 2 volt across them. Am I right? Yes. Okay. So now the point is that we do the same logic with respect to body effect, which means that I have some sort of potential difference between the source and the body. Okay, so with body effect. Or did you confuse that just because I have shorted these two nodes and connected to the ground in the previous case? No, right? Yeah. So right now I'm just going to consider a body effect. Now that I have this value of Vn, now how will I draw the graph for my V out? I want to draw the same current. What happens to my Vs? We know that the current equation ID is generally proportional to, okay, so assume that we are in saturation region, okay, so any of it is related to my Vt. Okay, so now that I am wrapping up my gate potential and the source is also trying to follow, right? So when you compare the source is actually making a potential difference between the source and the body. Now the voltage difference is keep rising. What happens to the threshold value? That also increases. So due to which the current increases or reduces? Huh? Yeah, because it is VGS minus VT, right? So because of this quantity getting reduced, the current value is getting reduced. So how will I keep up this current to be same? I don't want this quantity to get reduced, which means that the value of VGS is supposed to rise up. How will I make this VGS larger? Yeah, I have to make a large gap between the source and the gate. So which means that you will get a graph something like this, a kind of curvature. Okay, is that clear, making sense for your V out?